Morty. And the title of the talk is In Situ Investigation of Printing Immiscible Alloys Using Laser Powder Bed Fusion.
Good morning. My name is Brueggemann. I'm a junior majoring, or rising senior, majoring in material science and engineering at Clemson University. And this summer I worked in Dr. Morty's lab, the lab for advanced materials manufacturing, on the in situ investigation of printing immiscible alloys using laser powder bed fusion. Now there's a lot to break down in that title, so I'm going to start very simple and progressively get more complicated. So I'm sure you're all familiar with alloys. They combine the material properties of different components to improve upon the parameters of the original. I'm sure you're also familiar with miscibility, like this oil and water that refuses to stay mixed. Now our project was looking at immiscible alloys. Specifically, I was working with aluminum and tin in a 50-50 ratio, and these tend to separate out into their component phases due to a large miscibility gap in their phase diagram, as you can see here. They like to separate out. This is because of changes in liquidus temperatures, as well as density and surface tension and their crystal structure. Now, we wanted to make this look more homogeneous like this. And there are two ways to do that are commonly researched. The first is mechanical alloying, where it's a bit expensive and there are a lot of problems that come into solid state transfer of powders. So we looked at rapid solidification, which is the other method. We did this through additive manufacturing, specifically laser powder bed fusion, where there's a powder layer on top of the substrate and a high-powered laser or heat source selectively melts it. The trials we did were in one spot, which was spot welding, or across a single layer line scan. As you can see, it was a system much like this, where you would have a powder bed and a metal substrate and the laser up there. Now, to characterize this, you would often characterize it after the fact and compare that to your parameters for future experiments. We wanted to study it in situ, so we used a high-speed synchrotron source, which had a high-speed camera at the other end to give us an idea of what was happening inside the melt pool. So where does my project come in? I wanted to understand the phenomena within the melt pool by finding a link between the initial print conditions and the final print properties. I also wanted to quantify the homogeneity, the solidification, and the mixing within the melt pool. So what are you seeing in these images? What are you looking at? These are X-ray radiographs taken at the Advanced Photon Source at Argonne National Lab. The scans reveal different microstructures rather than different colors, because again, we're seeing, not colors, materials, because we're seeing an X-ray scan. I also want to point out the time. The entire print takes place in under 2 milliseconds, and the length, if you see the scale bar, the entire length is less than a millimeter. For purposes of clarity and definition, we used filters to remove extraneous distortion and improve the brightness and contrast. The first thing I looked at was convection currents within the solidification. So Marangoni convection, due to the temperature gradient from a high-powered laser, caused a lot of fluid to flow within the melt pool. This energy inputted from the motion across the powder meant that it was moving even faster in the line scans relative to the spot welds. Next, I looked at the solidification of the spot weld and found that after the laser turns off, the solidification front moves radially inward and the melt pool stabilizes, and it appears to separate out slightly by phases. So we also looked at the solidification of the line scans and found that the laser moving across had a higher impact on the velocity of the fluid. And the melt pool appears to remain mixed as the solidification front moves horizontally rather than radially. So to quantify these, the solidification front velocity was 89% faster in the line scan compared to the spot welds. So we'll be focusing on the line scans for the rest of the presentation. We also wanted to quantify what was happening across material systems. So we looked to dimensionless numbers, and because we didn't have temperature data, the two that we settled on were the Weber number and Peclet number. The Weber number is a ratio of inertial forces to surface tensional forces. It's essentially a measure of how much turbulence within the flow, and the mixing is overcoming the surface tension of the component liquids. The Peclet number is a ratio of convection to conduction, and a large Peclet number indicates that convection is more dominant. We wanted to compare those values to a degree of homogeneity. So we had these SEM scans from scanning electron microscopy, and we drew lines across various points and then created these line charts of grayscale values versus distance across. And then I used two methods to try and quantify homogeneity from this data. The first was looking at the standard deviation, because when it was more standard, it was more consistent with a single gray value, and the standard deviation would account for more homogeneity of the data itself. So in a scan like this, you would have something like that. And the standard deviation was averaged across a number of scans across a number of pictures. And we found this trend that showed that a higher Weber number, which you'll remember is increasing turbulence within the melt pool, led to better homogeneity as a lower standard deviation of these grayscale values. However, this doesn't tell the whole picture, because it could be well mixed and still have a high level standard deviation if you had dendritic structures where it was well mixed. So the second method was to look at the number of peaks, because if it was well mixed, you would have consistent peaks throughout, whereas if there was a point that was more aluminum or more tin heavy, it would have an inhomogeneity like this. And graphing that, we found a similar trend where there was increasing Weber number associated with an increased number of peaks. And this is, of course, graphed relative to the ratio of laser power to scanning velocity. So you may be asking, why does this matter? Why were you studying this? The larger purpose of studying immiscible alloys is it indicates a future frontier of advanced materials that you couldn't create by previous processes. And to put that more concretely, the aluminum and tin that I was working on is expected to be used for applications like bearings, because you could create an alloy with lower coefficient of friction than conventional aluminum and higher strength to weight ratio than conventional tin. Another example is one that my graduate mentor is working on, which is an iron magnesium system that could be used for intentionally biodegradable metallic implants, where there would be fewer surgeries because you wouldn't need to remove the implant after the fact. So the data suggests a correlation between a higher Weber number and a more homogeneous final print based on the available data that we have. More trials will certainly be necessary to develop an actionable conclusion on this, and also for more material systems and a larger range of printing parameters. My hope is that this framework will be helpful for future experiments, although those will most likely need to include thermal data so that we understand the temperature gradient within the melt pool over time, because there is great potential for immiscible alloys. I also want to thank Dr. Morty and my grad mentor, Hula, as well as Morty Research Group, Cornell, and the National Science Foundation. Any questions?
You got to it before I did. Any questions?
Yes.
Why did you want
The 50-50 ratio is, I believe, is essentially a starting point so that we could develop a reliable way to print it, and then once we could optimize those properties by changing the ratio. Yeah.
what benefits do you get from making an alloy more homogeneous compared to allowing it to be sort of separated?
You get more consistent sort of uniaxial, like directional properties. So it'll have the same properties in different areas and in different directions, rather than if it was separated out by phases.
Okay, thank you.
Any other questions? So I have one question, which
Yes.
is, would the lasers be used for mass production of these alloys, or is this really just a testing procedure? Or
It could be used for those mass productions, although the laser is, while it is a laser, it's essentially a heat source is what's necessary. So there is laser powder bed fusion on an industrial scale. I think GE uses it for an important piece in their engines, but it's merely a heat source, so you could use other sources for that.
any other questions? We have time for a quick question. Yeah, sure.
Could you elaborate a little more on, you were talking about like the biodegradable implants, like how would it be biodegradable?
So the idea is by tuning the magnesium content, the magnesium would slowly diffuse into the body, and you could potentially create an implant that slowly was just taken away by your blood over time.
That's so cool, actually. Thank you.
Okay, let's thank our speaker again.